special now, don't you? Once again, the word mole represents a number. The reason, well, we'll get to that when I get the actual number. What are some other words? You said pi, you said decade, which represents 10, but that represents a specific, a specific thing. The mole can mean anything. But anyway, what are some other things? Other words? Pardon? What number does X represent? Right. No, see, this is different, though. Then it does not represent a number. Does pi represent a number? Does decade represent a number? Yeah. Other words that represent a number. You guys are skipping the really, really obvious one.
Literally just 1, 2, 3.
Oh, okay. No. A quantity. That also just happened this year. That's a new one. That's just this year that one came up. Anybody have breakfast this morning? Who had breakfast? No one had. Oh my gosh! What did you have for breakfast? Don't say Pop-Tarts.
I forget.
Oh.
A muffin.
Oh, a muffin. Okay. All right. Anyway, nobody else had breakfast. What did you have?
Cereal.
Okay. Thank you. Everyone hear what he said? Dozen. Where was I going with that? Eggs. Okay. Does the word dozen represent a value? Yeah. What is that value? Thank you. How about a ream? What does the word ream represent, number-wise? For example, a ream of paper. By the way, this came up in the In the Know match on Wednesday night. It is! Ding, 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 ding. Speaking of office supplies, what if I wanted a gross of pencils? You've never heard that before, have you? You just don't know what the number is? That's right, but you have heard that. Okay. Does anybody know? 12 dozen or 144. Okay? But anyway, where I'm going with this is, you guys are somewhat familiar with words that represent numbers. Okay? That's all the mole represents. It represents a number. That number is this. .022 times 10 to the 23rd. Do you remember how I taught you how to use your calculators for the scientific notation? Yeah, there's a reason for that. You're about to discover that. We're going to do this a lot. Okay? Anyway, what would you say about the relative size of that number? That quantity? It's a little big. That value is so incomprehensibly large, you guys don't have any way of even contemplating it. It's just so big. I mean, you guys are somewhat familiar with million and billion and trillion, right? What's a trillion in scientific notation? 1 times 10 to the 12th. That's more than a trillion. Okay? I mean, it's incomprehensibly large. Okay? So why does that number have to represent such a or why does that word have to represent such a large number? Because the things that we deal with in chemistry are very, very, atoms, electrons, molecules. Has anyone ever seen an atom? Electron, right, okay? So just to give you an idea, let me make sure this is still right. Oh my gosh, it's not. The water must have evaporated. You guys think that all these stupid little things that I do have absolutely no meaning whatsoever, right? Yeah. It comes up all the time. There we go. Right there are 6.022 times 10 to the 23rd molecules of water. Not very much water, is it? Okay. Why does it have to have such a large number? Because molecules are very, very small. Okay. Now, I put the word particles here because as the year goes on, the word particle could represent anything. It could represent pencils. It could represent Parkers. We don't want that to happen. It could represent atoms, molecules, electrons, whatever. Okay. So I just put particle because you can have a dozen of anything, right? You can have 6.02, you can have a mole of anything. So I just put particles, and then we'll change that word depending on what it is that we're talking about. Okay? Anyway, like I was saying, very, very large number to represent. So now we have to represent a quantity that we can actually do something with in this class or a lab type situation. We now have a value that's going to get us up to that quantity. Now, what's that going to do with us? Why are we spending all this, other stuff with the periodic table, with the average atomic mass and everything? Somehow or other, we have to go from these particles and the mole to masses. Okay? So as it turns out, every single average atomic mass on the periodic table is based on one isotope of carbon. I don't know if we spent any time. Did we talk about the 3 isotopes of carbon yet? Did I mention carbon dating in here once? Okay. You don't have to write this down, but there are 3 isotopes of carbon. I'm pretty darn sure I did this in this class. Okay. Those are the 3 I did do this? Yeah. Those are the 3 isotopes of carbon. Carbon-12, carbon-13, carbon-14. Carbon-14 is the stuff that's radioactive. We talked about that. By measuring the rate of decay of the carbon-14 and how much carbon-14 is in a sample of substance, we can get a pretty good idea of how old that is. Okay. Anyway, the mass of carbon-12 is 12 AMU. Okay. Every single other atomic mass, every other single isotope is relative to this. This has been designated as the standard for the entire periodic table. So, if we have exactly 12.00 grams of carbon-12, we have that many particles. So there's a So that's our way that we're going to get to the mass that are on our periodic tables. So 1 mole is equivalent to the average atomic mass of any one element. And if we have that mass of that element, that means we have 6.022 times 10 to the 23rd atoms. So now I have 3 things that are equivalent to each other. Guess what we can make out of any 2 of those? Well, what did we spend most of the first chapter doing? Okay, you don't have to answer that question. They're not very talkative, are they? All right, moving on. So, for example, Kaylee, do you have a number I could use? And Taquana, what's your favorite element? She's going to say gold. Favorite element? Oh, come on, just pick an element. You have 118 choices. No, that's not an element. I've done this for a really long time. Taquana, by the way, I told them she's going to pick gold. Anyway, let's convert that to grams. And you're kind of, look, that's a good look. You and 8 other people did the same thing. Now, how do we convert one thing to anything? What have we used all year long so far to convert one thing to something else? Say conversion factor. A conversion factor. And what is a conversion factor? It's made from any 2 things that are equivalent to each other. Would you guys agree? I currently have 3 things that are equivalent to each other. You can pick any combination of any 2 of those to make a conversion factor. In this particular case, which 2 of the 3 am I going to need? Go ahead, Emily. We're going to need the mass because I'm trying to find mass, definitely. What's the other one I'm going to need? What's that word right there? What's that word right there? We're going to use that. Okay, so here we go. So go start off with 3.04 mole. Oh, by the way, I know this doesn't help much, but you're going to see it, and I don't want you getting your panties in a bunch when you do. There's the abbreviation for mole. I know. I'm just get used to it, okay? So anyway, 3.04 moles of gold. You're going to make a conversion factor. What's the relationship between moles? What is the average atomic mass of gold? It's right there in your handy-dandy periodic tables. 196.97. So we're going to put that in the numerator. What's going to go in the denominator? 1 mole. Clearly, my moles cancel. You do a little multiplication. 3 times 200 is a little under 600. It's going to actually be right at about 600. Would you guys agree? Sure. Could someone, let me see, who's going to be my designated calculator people today? Looks like Quentin and Dora. You 2 are my verifiers. We're going to do, the rest of us are going to estimate all day long. No. Dang it. Hello, Mrs. Couchet. Haley is here. Well, I got all kinds of issues here then, don't I? All right, thank you. First of all, it wasn't who it said it was. I don't even know who Kim is. 2, jeez. All right, so anybody have, okay, who are my designated calculator people? You and you, what'd you guys get? Okay, so now we're going to have the discussion of how many significant figures are going to be valid. 3. So this is going to round to $5.99. Now, before we go any further, there's the right answer, 599 grams of gold. I do want to say this. I have to strike a balance between making your life as easy as possible. Believe it or not, I actually do try to make your lives easy. It seems weird, but I actually do try to make your lives as easy as possible. But 2, give you enough information in these values that we're using, okay, that they're not going to limit our significant figures. Okay, I want the measurements to limit our significant figures. So with that being said, from this point forward, any atomic mass that you pull off the periodic table, round to the 100th place. Many of them are already to the 100th place. For example, I think this one was, wasn't it? Wasn't it 196.97 on the periodic table? Many of them are. There are a couple, though, that are going to cause you some problems historically, and so I want to point those out real quick. Oxygen on your periodic table is written as 15 point, probably either 999 or 9994. I can't remember which one. 999. So therefore, the 2 significant figures, what is oxygen's average atomic mass going to be? To the 100th place is going to be 16.00. I believe fluorine is probably written as 18.9978 or something like it. Okay, so we're going to round that one to the 100th place to 19.00. Do you see where I'm going with that? Do they have, let me see, is chlorine 35.453? Or is it 35 just 45? Oh, okay, they already did that one for you. Sulfur, do they have it as 32.06? Oh, so they already got that one done for you. Oh, phosphorus usually causes... No, actually it's potassium. What is potassium going to be to the 100th place? .10. Okay, anyway, do you guys see where I'm going with that? Those are usually the ones that cause the problems. Okay, moving on. Does anyone have any questions on this so far? I mean, you know, it's a conversion factor. Okay, let's try a couple more. Oh, Destiny, a number? Oh my gosh, are you kidding me? I'll show you then. And Hudson, your favorite element? Who? No. Come on, be creative. Thank you. Did you say fluorine? Chlorine. Okay, and let's convert this to moles. Oh, by the way, before we go any further, saying 6.022 times 10 to the 23rd gets to be a pain in the rear end all the time, doesn't it? Right. So, this was actually, like so many things in science, named after some old dead person. Does anyone happen to know who the old dead person is that they named this number off of? Or over? Say this again? Mr. Mole? No. It's referred to as Avogadro's number. It's possible in one of your math classes you may have been introduced to this. Possible. Not likely, but possible. He is a former, well, he's dead now, like I said earlier. I'm going to guess in the 1600s, but I can't remember when, late 1600s. Anyway, he was an Italian mathematician. Turns out mathematicians, scientists, they were all the same people anyway, okay? But they attributed this number to him or named this value after him. Anyway, so here we go. What are we going to start with? Oh, before we do that, which two of these three are we going to need to make our conversion factor with? Anyone can shout it out. Don't be shy. What's that? 1 mole, because we're looking for moles. Were you given a mass? Were you asked to find a mass? No. So therefore, no mass. Get it? Thanks. No, seriously, no mass. If you weren't given a mass, you're not asked to find a mass. Do we need the mass? No. Were we given number of particles? This time the particles were atoms. So here we go. We're going to use these two. So 5.082 times 10 to the 21st atoms of chlorine. What's going to go in the numerator? If you guys all shout it out at the same time, it cancels the noise out. Okay, so just one at a time. I'm sorry, what? Excellent. 1 mole. And what goes in the denominator? How many atoms? Say it. No. I just gave you the easy way to do it. Okay, Avogadro's number, 6.022 times 10 to the 23rd. There you go. once again, other than Quentin and Dora, do not touch your calculators. Let's make a quick estimation. What is this answer going to be? This is actually going to be one of our early opportunities to start reminding ourselves of the decimal equivalents of fractions. Does anyone know what the decimal equivalent of 1/6 is? I guess not. It's right around 0.12, okay? But we have 5/6. So around 0.8-ish or so, okay? So our answer should be right around 0.8-ish. But look at our exponents. Do they match up? 21st, 23rd. No. So it's probably going to be 0.008 since there's a difference of 2 there. So, handy-dandy calculator people, let me know what you got. You know what? The rest of you desperately need practice for getting numbers into your scientific notation, into your calculators. You guys might as well practice too. I'm not entirely convinced of your abilities to do that yet. But, Clinton, what do you got? Oh, you did it wrong. I'm sorry, what?
How would I put that?
Do you have your calculator?
Yes.
I showed you this, believe it or not. Yes, I did.
Why? I got it.
What do you got? What do you got, Ben?
0.0084390.
0.0084 39
0.
Okay, we're good. Because we have 4 significant figures in our value over here, 4 significant figures here, moles.
I know how to do scientific notation.
There you go. Okay, so was our estimate of 0.008-ish pretty good?
Yeah.
Yes. You guys need to know your decimal equivalents of fractions. Okay, let's try another one. Parker, number.
37.45.
And Luke, your favorite element.
Hydrogen.
Oh, dang it. Oh, come on. Let's be a little bit more creative. Nickel, excellent. And let's convert those. Oh, darn it. We are like a day behind. We're 10 minutes behind. 10 minutes.
We're 10 minutes behind.
We're 10 minutes behind.
Dang.
All right.